like to present my research on the topic analysis and numerical simulation of the Kawahara equation with a moving boundary. This work was supervised by Dr. Berikbol Torebek. Here is the outline my presentation. First, I will start with the introduction and probable statement. Then I will present the theoretical results concerning the exact uniqueness of solution. Finally, I will discuss the numerical solution and present the computational results. Let's begin with the background. The famous cordon-free equation describes weakly nonlinear long waves. However, in a quasi-critical regime, for example, when the bound number approximately one-third and the third order dispersion coefficient becomes small and the visual balance degenerates. To address this, we need high order asymptotics. This leads to the Kawahara equation. This equation, called Kawahara equation. The equation is essential when the third order dispersion nearly vanishes. Our work especially addresses the challenge of solving Kawahara equation in non-cylindrical domain. Picture
Could
one.
you change slide?
Slide. Slide not moving. Slide. Only we see first pages.
Не понял, простите, I don't understand this question. Слайд не видно?
Only first pages.
Only pages?
Yeah. Only your
okay.
title of your talk.
Okay, 1 minute.
Okay.
Now it is okay.
Okay?
Uh-huh.
Okay, sorry. I didn't know.
Okay, please start with.
Okay. Okay. Let's begin with the background. The famous equation, coordinate equation,
Пока не видно
describes
слайда.
weakly nonlinear long waves.
Нурбол, нету слайда пока.
Пока нету?
Да.
Теперь? Теперь видно или?
Yeah.
Да, видно.
О, ендерс.
Переключается, да?
Да, ага, переключается. Ушинши боктор хазыр.
Yeah, sure. Excuse me. Sorry. The famous coordinate equation describes weakly nonlinear long waves. However, in a quasi-critical regime, when bond number approximately one-third, the third order dispersion coefficients become small and the visual balance degenerates. To address this, we need high order approximate this 5 order term. This leads to the Kawahara equation, which includes a 5 order derivative term. This equation is essentially when the third order dispersion nearly vanishes. This equation called this Kawahara equation. Our work specially addresses the challenge of solving the Kawahara equation in a non-cylindrical domain. As shown in Picture 1, we consider a domain where the boundaries alpha of t and beta of t change over time. This creates a moving boundary problems, which models physical phenomena like dispersive spreading and nonlinear stepping in a changing environment. Recording previous work, first evolution equations on moving domains have been studied for the BBM equation, coordinate equation, and Burger's equation like this. Second, regarding the Kawahara equation, special control theory is less developed compared to the KdV equation. While some authors like Daronin and Larkin have been studied exactness on fixed domain. Our work investigates two new aspects. The first part, analytical part, will prove exacts and uniqueness in a moving domain. Second part, computationally, we develop a numerical method for this problem. Here is a mathematical formulation. We study the Kawahara equation given by equation 1 in a time-moving interval, Q2. We impose boundary conditions on the moving boundaries alpha of t and beta of t, and initial condition at time 0. We assume that the interval length is bounded and never collapses at 0. The first main results, first theorem, to obtain regular solution, we impose compatibility conditions at the boundaries. Conditions 2. And our main results is the following theorem 1. Let initial data V0 belong to subble of space H5. Then for any finite time t, the exact unique strong solution to the problem. The solution satisfies the regularity classes shown in equation 3. Second main results, we also present a K theorem regarding the global stability of the solution. We assume that the boundary functions phi and the velocities of the moving boundaries alpha and beta are integrable, are bounded. The main result states that if the initial data and boundary forcing are sufficiently small specifically, if the combined norm is less than a small parameter delta, then two important properties hold. First, the strong solution V of t exacts globally in time, and second, the solution decays exponentially as time goes to infinity, as shown the final inequality. The first, to analyze this problem, it's difficult to work directly with moving boundaries. Therefore, we use diffeomorphism F, defined by 4. This transforms our time-dependent domain Q2 into a fixed cylindrical domain Q with X variable. Furthermore, to use the Galerkin method, we need to handle boundary values. We introduce a new function, Ux to bring our system to homogeneous boundary conditions. This transform is crucial for constructing the approximate solution. To prove the exact of solution, we use Galerkin method, and however, to ensure convergence, we first introduce a regularized problem. We add an artificial 6th-order dispersive term with parameter nu. This term provides the necessary viscosity to make the operator uniformly parabolic and allows us derive a priori estimates. We construct approximate solution UN using a special basic of eigenvalence function omega g. The coefficient g at t are determined by solving a system of nonlinear ordinary differential equations shown here. This allows us to find a finite dimensional approximate to the solution. Our strategy consists of 3 main steps. First step, for a fixed nu, we prove the exact of solution to the regularized problem. Second step, we derive uniform a priori estimates that are independent of the parameter n and stable as nu tends to 0. Third step, we pass to the limit. First, we let n go to infinity to solve the regularized PDA, and then we let parameter nu go to 0 to obtain the weak solution of the original Kawahara equation. Here we derive the necessary energy estimates. The first estimate independent of parameter nu, and it gives us control over the L2 norm of the solution. Second estimate depends on parameter nu and provides higher order regularity control. These estimates are critical for the compactness arguments. We also need to control the time derivative by differentiating the system with respect to time. We derive the estimate shown here. This proves that the time derivative ut is uniformly bounded in the L2 norm. This ensures the solution does not change too abruptly in time. Using these estimates, we can pass to the limit as n to infinity. We obtain weak convergence of the solution and its derivative. However, for the nonlinear term u at x, a weak convergence isn't enough. Isn't enough. We use the Alban-Linz compactness lemma to obtain strong convergence, which allows us to pass the limit in the nonlinear term. And estimates independent of parameter nu. The first estimates. Similarly, we derive a uniform estimate for the time derivative ut. Assembly in the initial data is sufficiently smooth. We show that the norm of ut is good. Now we need estimates that don't depend on the regulation parameter nu. We use weight energy method. Energy function, energy method, our multiplier function e x degree. And applying Cron's lemma, we obtain the uniform bound shown in the equation where the constant C4, excuse me, constant C4 doesn't depend on parameter nu. Second, estimates independent of parameter nu is similarly, we derive a uniform estimate for the time derivative ut. Assuming in the assuming in the initial data is sufficiently smooth, we show that the norm of ut is bounded by a constant independent of parameter nu. This justifies the final limiting process. Finally, we let the regularization parameter nu tend to 0. We extract a subsequence u nu that converges to the solution u. We verify that this limit satisfies the original equation boundary conditions. Those density arguments, we exact these results to initial data in H5 and completing the exact proof of theorem first. Second, Next slide here shows uniqueness of the solution. To prove uniqueness, we assume there are two solutions, U and tilde U, are considered U tilde and U double tilde, and consider the difference nu. Then V difference. V satisfy an equation is zero initial data. Using the weighted energy method, again, we derive the inequality shown at the bottom, since the integral starts at zero, and with Gronov lemma implies that nu must be intensity zero. Therefore, the solution is unique, and we prove it the first theorem. We also study the stability and long time behavior of the solution. First, we establish a global bound on the L2 norm, as shown in this inequality. And solution remains bounded for every time, provided the source term is controlled. And for exponential decay, under a small data condition, we can prove exponential decay. With a Lyapunov functional with a specific weight g of at x, this leads to the differential inequality shown here, which implies that the solution decays exponentially to zero as time goes to infinity. And we prove it theorem 2. Now, now let's move the numerical solution. In this section, we construct a numerical scheme to approximate the solution of the Kawahara equation. Although the original problem is defined in a moving domain, we perform the simulation on the fixed cylindric domain with deformativism F. For the purpose of this numerical simulation, we specifically consider the problem with homogeneous boundary condition. And the equation 6 shows the resulting system with the variable coefficient axt and b of t. In numerical part, we consider only homogeneous boundary condition in system 1. We apply the Galerkin method to this transformer system, multiply by the test function omega, and integrating, we obtain the variational formulation shown in equation 7. We approximate the solution UH as a sum of basis functions phi here omega g, sorry, with the time-dependent coefficients d, e at t. Substituting the basis functions into the variational form, we derive a system of equations involving with matrix A, B, D, C, E. And these masses respectively be mass and stiffness and high-order derivative term. The results in the nonlinear system, ordinary differential equation shown in equation 10. Here, G at T is combines the linear term and term with D second. This represent to non-linearity. To solve this system in time, we use the Crank-Nicolson scheme to handle the non-linearity efficiently. We linearize the tensor term C. We approximate the values at time Tn plus 1 and Tn using the average, which is characteristic of the Crank-Nicolson method. After this leads to the linear algebraic system shown here. At each time step, we solve for the vector Dn plus 1 using the null values from the previous step Dn. The matrix on the left-hand side, this matrix is non-singular, allowing us to proceed iteratively. For the special discretization, we use uniform quartic B-spline for degree. Our basis function. These splines have compact support and provide high-order accuracy, which is necessary for the 5-order Kawahara equation. And since we have homogeneous boundary conditions, we modify the standard B-splines to satisfy zero conditions at the boundary x equal to 0 and x equal to 1. We define the basis function phi as shown equation 11. This ensures our numerical solution satisfies the boundary conditions. And to evaluate our method, we consider test problem with a known exact solution. We choose the moving boundary alpha of t and beta of t defined here. We construct the coarse term g at xt such that the function uxt is the exact solution system 12. And here we compare the exact solution red line and numerical solution blue dashed line. And with just here 10 basis functions and time step of 0.01, we already see reasonably agreements at different times, and though some small deviation is visible. When we increase the numbers of basis function 30, m equal to 30, and time step 0.005, the results improve significantly. As we can see in figure 5 and 5, 4.5, the numerical solution considers almost perfectly with the exact solution. And this comparison confirms that the error is negligible. The perfect overlap demonstrates the convergence of scheme as we refine the mesh and reduce the type set. And we quantified the error using the 14 norm. Table 1 and table 2 show that as we inscribe m and describe delta t, the error decreases rapidly. For example, with m equal to 0, the error is on order of 10 degree minus 6. This confirms the effectiveness and high accuracy of our method. And this 3D plot shows the numerical solution xt and system 12 when g at xt equal to 0 in fixed domain. Next 3D plot shows is VM YT is a numerical solution of system 1 with homogeneous boundary condition and is moving original physical moving domain. This concludes my presentation. Thank you for your attention. I am happy to